we had the last of the racket assignments with the higher order functions and more higher order functions. Hopefully everybody got those turned in. Last week we also started our introduction to our unit on interpreters. So we talked about, first off, Julia, just to introduce the language that we're going to use to implement them. There's nothing magical about Julia for interpreters. So again, don't think that you have to be writing interpreters in Julia. We chose it, one, because it is yet another different language for you to see, but also it actually has some nice things that you'll see as we go that actually make the, once you understand what it's doing, it's actually somewhat simpler to write and to read and understand some of what the interpreter is doing when you write it in Julia. Although I said that there's nothing magical, there are some languages, you know how there's sort of certain languages make certain jobs easier. Certain languages, it's easier to write interpreters in, and some others it might be harder. And so it just, we hopefully chose it as a good language. We also talked about the general structure of programming languages tools. Remember that diagram of compilers and interpreters and JavaDoc and language translation, all kinds of other things. And then last time on Friday, we just started building our own interpreter. So first off, any questions before we dive in? Any questions that you have? Okay. We hadn't covered everything by Friday for you to start on the interpreter. Well, if you wanted to look ahead and look at the code that I distributed online, you could start. But hopefully you didn't mind having a weekend off. So I'm sure you've got things with other classes. So in terms of other calendaring things, though, most of you are probably aware that this is the STEM fair. And so how many of you are going to be over there and hopefully getting interviews this week? Okay, that's kind of what I would expect since you're mostly juniors and seniors. Seniors, of course, you're looking for full-time jobs afterwards. Juniors, hopefully you're looking for internships during the summer. Some of you seniors may not be looking for jobs because you did internships and came back with an offer in your pocket. That's the best way to do it. So even if you're not immediately on the job market, I would definitely recommend at least going over and walking through, talking with employers, participating in the various information sessions and other things this week. Let me also just, a little bit of advice in terms of some of the job market. One, I know that there are some companies really competitive to try to work for, but in general, the companies are competing for you all. Tech is booming. They are hiring, and they want to hire good students, and you all are good students. And so remember that an interview goes both ways. They're not just interviewing you for the job, but you're interviewing them as an employer. Also, if a few really intelligent questions that way can not only be useful for you, but it actually shows them that you're taking that side seriously as well. Also, it's really easy to just focus on the companies that make the products and services that you're used to using, right? So you all know, the Apples and the Amazons and the Microsofts and Googles and Facebook of the world, right? You know all those companies. There are tons of other companies doing really cool things in technology. Look at some of the national labs like Sandia or Lawrence Livermore. Some companies that do a lot of defense contracting work, Lockheed Martin and others, actually also do some very interesting work. There's also a whole category of companies that's easy to overlook. And the main reason is, if you actually look at it, more software is written for in-house use than is sold. And so there are a lot of companies that do financial systems, retail, all kinds of things like that, that aren't so much about developing software to sell, which is why you may not have ever heard of their software, but they're developing it for in-house use. So ExxonMobil is doing some really cool things with things like visualization and other tools for exploration for oil, and other kinds of things that they're diversifying into. You probably wouldn't have Walmart at the top of your list. You know, most students I know are thinking, yeah, I didn't go to college for 4 years to go work at Walmart. But I've had former students who've gone to Walmart, and if you think about it, all the technology that goes into trying to manage a global supply chain on the scale of what Walmart does, they actually do some really, really cool stuff. Yeah?
My older brother actually went and worked at Walmart.
Uh-huh.
He's on a user experience team.
Oh, good.
I actually really enjoyed his job.
Yeah. See, I mean, if you look at what Walmart's doing, they're moving to compete with Amazon, at least in terms of a lot of the online e-commerce kinds of stuff. So there's the user experience for the websites, and there's also just all the internal stuff. Like I said, banks, financial systems, other kinds of things. So look at companies that aren't just the ones that make the products that you use every day. Look at all the other kinds of things, companies that are doing really cool things out there. All right, just wanted to give you that kind of a plug. So let's dive back into building our first server. So quick recap. Here's a simplified view of the diagram that we were working with last time. This is actually the flow for the interpreter we're building. So remember, we start with concrete syntax. That's the actual text that the user types in, the programmer, and that's going to fit some grammar. So for us, the language that we're doing is OWL, remember our WIDL language. Trust me, those who've come up with acronyms have tortured the language worse than that. So OWL, remember again, is based on just, it's a simple calculation kind of a thing. So it's evaluating arithmetic expressions. An arithmetic expression is defined to be a single number or paren plus two arithmetic expressions, close paren, or the same thing with a minus. And that's it to start with. So that's the concrete syntax. So you start with the grammar. Then we talked about, normally you parse that. Now, again, we typically break the parsing process into two steps. One is to just take the sequence of characters and chunk them into what are generally called tokens. This is lexical analysis, a scanner, tokenizer. I've heard all the terms used out there. What did they use in 236? Lexical analysis?
Tokenizer.
Tokenizer, yeah. Lexical analysis is the formal term. Tokenizer is quite common. Those who do it or who actually work with it often just call them scanners. You're just scanning the text, spitting out tokens. That part again, and did you write one in 236?
Yep.
Okay, it's just regular expression matching. This is where, if you think about it from a language design level, you get to decide what is a valid identifier in the language. What is the proper format for typing in a floating point numeric literal or anything else that you want to do. So again, we give you the lexical analyzer, and it's in a module just called Lexer. And it has one key function called lex. So last time I showed you what happens, and we'll go back and we'll do that again. So that produces a sequence of tokens. The parser then takes the sequence of tokens and is basically just trying to match the grammar. And so as we go through, the process of the parser is entirely, all right, which non-terminal am I parsing right now? In our case, it's just one, but it extends to multiple non-terminals. Which non-terminal am I trying to parse next, coming up? Which possible production could it be by looking at the first or the second, or depending on how far look ahead you want to go in terms of the tokens. We're trying to design ours so you can just look at the very first, the very next token, and know what you're looking at. The job of the parser then is to produce abstract syntax. And usually that's going to be in some sort of tree-like form. So the same way that the grammar is inductively defined, the non-terminal on the left shows up on the right. Well, that will be other pieces of abstract syntax. So everywhere where there's an AE in the grammar, there's going to be a piece of abstract syntax. Okay, and that's going to form a tree structure. Then finally, we're going to feed it into the part that actually does the calculation. And its job is just traverse the tree and spit out what the result is, actually do the math. and then finally we'll get results coming out. So that's the flow of what we're going to build. Oops. Here's how far we, whoops. Here is how far we got building it last time. So last time we defined the abstract syntax. Remember I said that we're going to, Julia works with what are called modules. That's sort of the highest level compilable piece. So we're using the lexer, so that's already given to you. We're also using, there's an error module that we define. It's the exception we're going to throw when we encounter an error. So we have, if you think about it, again, for the concrete syntax, we have a non-terminal AE and 3 possible productions. So what we want is an abstract type, a parent type, if you will, AE, that comes in 1, 2, 3 flavors. So every time we add a production to the grammar, we're going to add a new subcase of an AE. Now, if you had a grammar with 5 different non-terminals, then you'd have typically 5 different parent classes, and then however many I say classes, I'm thinking of it from an object-oriented standpoint. If it was object-oriented, you really would have, these would be classes in it, but you just simply have 5 different sort of parent types or representations, each of which would have some number of subtypes or subclasses if you're doing it object-oriented. Does that make sense? All right, now think about it for a language like C++. C++ has on the order of about 80 to 100 non-terminals. Some of those have just 1 or 2 productions. Some have, like statement has about 10 or 12 different productions. So that's the structure of your abstract syntax. It can be very simple, or it can get really, really hairy, but it follows the same principles. The structure of the grammar will drive the structure of the abstract syntax. Okay. The other thing we're going to see is as we're recursively parsing this to try to produce abstract syntax, excuse me, sorry, pardon me. As we're parsing it to produce abstract syntax, the structure of this grammar will also drive the structure of the parser. And so let's see what we mean by that. So first off, abstract syntax again comes in 3 flavors. If it's a number, we'll just simply remember, yes, it parsed as a number, so we need to remember which production it was, and then any other pieces of information we still need to remember. So in this case, what the number was. Here we'll remember this, they were doing addition, it's a plus node. We throw away the plus symbol, we throw away the parentheses. That's all just syntax. We just remember, they're doing addition. And here are the 2 sub-expressions, we just call it left-hand side, right-hand side, that they want to add the results of. And then likewise with minus. All right, so everybody okay to that point? All right, so let's start building parser. We're going to have a function called parse. Actually, let me go over here. So the lexical analyzer actually takes just a string of a string of characters. So we did a very simple one like this last time. And so what's going to come out again, so anytime you're writing the parser, it's always good to look at what's coming out of the lexical analyzer. So it will always return basically we're going to return Julia values that represent what was actually lexically analyzed. So we're kind of simplifying things a little bit here. If I just simply do something like, I'm going to store this one, but if I just simply store a numeric literal, what's going to come back is simply the Julia value 5. So it'll either come back as a single number or an array. So let's write these cases. Now, we could write, so we'll write the parser. Function parse takes as input something that we'll just call an expression, We're going to return an abstract syntax tree out. Now, by the way, Julia actually has its own internal type expression. It can sort of talk about, using expression and symbol, it can actually talk about its own grammar. That's why we're kind of leveraging a little bit of that. So we could just parse and take an expression in, and then what's the first thing you'd want to do? So remember, that expression is going to be something like these outputs from the lexical analyzer. So what do you want to do? Yeah.
You just want to see if there's an operator or if it's just a value.
Right. So if it's just a value, what would it come in as?
Number or
Yeah,
something.
yeah, a number. Or if you're a lot of scanners or tokenizers will actually have sort of a token class or type that stores what kind of token it was and then other information. So the first thing you want to do is just look at what's that first thing coming in. Yeah.
Is that expression the string or the array that you got back?
The array that you get back.
Okay.
So the idea is we're going to feed it through the lexical analyzer, and so the sequence of tokens is what's, sorry, I realize it's hard to see the board now that I brought the lights down, but the sequence of tokens is what the parser is going to take as input. So our first question is just simply, is it a number or is it an array? Okay, that's how these different things are going to come in. And then if it's an array, we'll need to look at the first element of it to differentiate it. So we can actually use type of to do a whole bunch of type of tests here. It's actually easier, once you kind of get the hang of it in Julia, to actually just use that multiple dispatch that we talked about before. So let's write a parse function that works on a number, a parse function that works on an array, and so on. Okay. One of the things, by the way, that's useful if you get into multiple non-terminals, you probably saw this in 236 when you're writing recursive to Sept parser, which is what we're doing. Write one parse function for every non-terminal. So in C++, you'd have parse statement, parse expression, parse term, parse parse while loop, and so on. And those just call each other with mutual recursion. All right, so if we're parsing a number, what do we want to return? Yeah? A num node, exactly. So in other words, we determined, the fact that it simply dispatched to this function means it's this case. And in that case, we want to return the corresponding abstract syntax. So the job of a parser is always return a piece of abstract syntax. Now that might have other pieces hanging off of it based on the recursion, but that one function generally shouldn't worry about that. So we will simply return, actually I'll put it here just for readability. We'll return a num node and we'll store what the expression was, what the number was. In fact, the fact that it dispatched here means that this expression is a number, and that's what goes in there.